Fine. So let us begin. This class will be pretty much interesting because you will be starting to visualizing the things, right? Why I'm saying it will be more interesting than previous classes. So in previous classes, you started with how our course started for nonlinear dynamics. What we did is first we did study 1D maps, right? We studied 1D maps. Now the idea is like one-dimensional maps you cannot really visualize because the 1D maps will be just like numbers and numbers one dimension. So they will just lie on the real line. They will just lie on the real line. Either it can lie here on the positive side, like we see some things like, yes, now it is here. Next iteration, it might be here. Next iteration, it might be here. Further iteration, it might be here. Like, right? You understood? So like that, we understood how the dynamics is. Now based on that, we classified attractors, right? We classified into attractors. What are the attractors possible? Like you can see, it can be 0, it can be 1 plus 1, point can lie here. Then after that, it can iterate back to another point, that is minus 1, right? So again, when you iterate it, it might come back to 1. So that is like a periodic orbit. That is like a periodic orbit. So what is the period of this orbit? 2. Why? Because you started from 1. When you do the next iteration of the map, right? How the map looks like, xn plus 1 is f of xn, right? So you are at 1. When you iterated the map, it is minus 1, right? Again, when you iterate the map, it is again plus 1, right? So it is in between minus 1 and 1. They are oscillating, right? So therefore, it is a period 2 attractor, right? And what other things we discussed? It can stay at one point only. It can stay at one point only, right? I mean, this is x star, and however you iterate, how much you iterate, it will just stay at x star. It will not move. So it is fixed at x star. So we call it a fixed point, right? Now, what other scenario we could have? Another scenario is like it is here, then it went here, right? Then it went here, then again this went here, it went here again. So there is no definite pattern, right? However, it is not random. However, it is not random, right? So why it is not random? So because it is behaving like a chaotic orbit. Okay, so this is known as chaos. Like it is sensitive to initial conditions. I mean, if your starting point is just a minute change in difference, the whole trajectory will again be different. The whole time series will be totally different just by a tiny change in your initial conditions. So therefore, it is chaos. However, visualizing through this number line and cobweb, so we installed cobweb diagrams, right? We installed cobweb diagrams in our study so that we can easily visualize that whether we start from any point, is it a period 2 orbit or whether it is a period 3 orbit. Okay, it is a period 3 orbit. So we'll see. So, but however, there are some limitations. However, there are some limitations to this. Okay, what are the limitations? The limitations is like we cannot visualize it. It is very difficult to visualize on a single number line, right? So when it becomes interesting, when your dimension increases, right? So now if suppose I tell you 2D maps, then these are pretty interesting. Why? Because now instead of a one variable, you will have two variables. Instead of one variable, you will have two variables. That is xn plus 1, yn plus 1. And this you will have some f1 of xn, yn. And this will be some f2 of xn, yn. Right? You got the idea. So why this will be interesting? Why 2D maps are interesting? Because whatever attractor will happen, you can easily visualize them on the 2D plane xy. You can easily visualize them on the 2D plane xy, right? Like how from one point you can evaluate the function, you can get to another point. You can then iterate the map f to go to another point. Iterate the map f and you can go to next point, right? Now, suppose you iterate this point again and now it came back to this starting point again, right? So what is it? It's a periodic point, isn't it? It's a periodic point. So what is the period? You did from one point, first iteration, second iteration, third iteration, and fourth iteration. In 4 iteration, it from where it started, it came back again, right? So therefore, it is a period 4 orbit, right? It's a period 4 orbit. When it's a period 4 orbit. So therefore, through this you can visualize. Through this, when it comes to two dimension x and y, you can visualize the dynamics. How the points are going here and there, you can visualize the dynamics. So you can visualize chaos. What is chaos and how chaos occurs in this system? You can visualize. So till now it was a bit difficult because 1D maps, you just have to do some mathematical computation like derivative less than 1 greater than 1, how to compute eigenvalues, right? But here it will be pretty interesting because you can see everything happening on the xy plane, right? So therefore it is interesting. So the idea is like we started off our course with the 1D logistic map. We started off our course with 1D logistic map. That is xn plus 1 is some r, that is reproduction factor into xn into 1 minus xn, right? So this kind of models the population dynamics of animals. So we understood this. So r is a parameter, and r you can have in between 0 and 1. That's a parameter. So r is a parameter, and when you vary r, it's like a remote. Okay, yeah, it's like a control parameter. When you vary r, okay, you will see lot of different features of the attractors, right? So that is 1D logistic map. Fine. So that's the idea. So fine. So now the question is, how can we create 2D maps? 2D maps. 2D maps. Okay. Any ideas? Any ideas? So in order to understand that, I will give you some ideas, right? So suppose this is a XY coordinate system, and this, sorry, you have this square box. You have this square box, right? So now my question is, you try to apply a transformation which can stretch it along x-axis. Okay, can you apply a transformation which can stretch it along x-axis? So if you apply a transformation like stretch along x-axis, so the idea is like what will happen, how it will look like. So it will look like something like this, right? So let us be perfect in this case. So we can see from here that it will be there. So it will be like, isn't it? Why? You can see the y-axis is pretty much the same. Y-axis is pretty much the same, isn't it? However, the x-axis has got stretched. The x-axis has got stretched, right? So what kind of transformation can you apply? So suppose any point here you can take x comma y, and that is being mapped to say x prime y prime. Then can we write x prime y prime in terms of x and y? Yes, we can write. X prime is say some b of x, and y prime is equal to y, right? You understood what is happening here. So we are telling don't disturb the y coordinate. The y coordinate should be the same, and it is same because you can see the same y coordinate is going on through the two figures. However, the x coordinate has shifted, right? So how it has shifted? It has shifted by a factor of b. It has shifted by a factor of b, and since they have expanded, we can easily see that b should be less than 1 or greater than 1. Greater than 1. Okay, b should be greater than 1. If b is greater than 1, then it can have the stretching property, right? If b is less than 1, it will have a contracting property, right? So if b is less than 1, what will happen? It will be another case like this. So you can see, suppose this one. So if it is contracting, you can have something like this, right? So x and this is y, right? Fine. So you can have b to be less than 1. Fine. You can understand. So here what has happened? Here contraction has happened, and here expansion has happened. Here expansion has happened. Fine. Okay. So therefore, but this cannot show chaos. Can this mapping show chaos? No. Like wherever you start with and stretch it, it will always get stretched. If you contract it, it will always get contracted. Right? So there is no point, like, so there is no unpredictability. There is no unpredictability. I mean, if you stretch, stretch. If you not stretch, contract, contract. But observe why that happens. Why it is so predictable. I mean, we can confidently say that if b is greater than 1, you can expand, and if b is less than 1, you can easily contract. How confidently can you say this, right? I mean, you can confidently say this because you are in a linear setting. You are in a linear setting, right? Why? You are in a linear setting because it is very linear. It is a linear map. All your variation here are linear. Your right hand side, every expression are linear, right? But things get pretty interesting the moment you have nonlinear terms. Things get very interesting, very interesting when you have nonlinear terms on the right hand side. Okay, so what's the simplest nonlinear term we can keep? Hmm? I mean, it is linear now, right? So what's the next simplest nonlinear term we can keep in our map? Hmm? Square. Yes. So this same idea, Henon applied. Henon said that yes, I can understand the dynamics of a linear map, fine, but there is no chaos and interesting dynamics because it is either contracting or expanding. So now what is the action of the map when I make it nonlinear? Right? When I make it nonlinear, what happens? Same idea when logistic map was done. Okay. Remember that I gave you a map that in 1D, I gave a map in 1D that is xn plus 1 is axn, right? Fine. You understood that if a is less than 1, it was converging to 0. It was converging to 0. When a is greater than 1, it was converging to infinity, right? So, therefore, 1D linear maps are also not interesting. So, therefore, what the scientists thought, how about we add some nonlinear terms? How about we add some nonlinear terms? And how come they add nonlinear terms? You can see there is an x square term, right? So you can see this logistic map where rxn minus rxn square terms are there, isn't it? Fine. Okay. So this is the idea. This is the idea. Hmm? So now my question is, can we create a 2D nonlinear map? Yes, we can create, because you told the answer that yes, our next nonlinearity we can add is a square term. So now the idea is clear. Can we construct a 2D map but with nonlinear square term? Okay, nonlinear square term, and if we put that square term, what happens to the map? What happens to them, right? So this is what we are, this is what Henon has studied. Michael Henon has studied this, and when he framed the map, the map was called to be the Henon 2D Henon, right? So what he did is the similar way I showed you. Let us use some other color, maybe this one. Okay. So what he did is these are xy coordinates. Okay, these are xy coordinates. Fine, these are xy coordinates. So you have maybe we'll draw in a different way. So you have this xy. Okay, you have this xy strip. You have this xy strip, right? Now the question is, actually, before going to this, the chaos property. So whenever chaos is there, how chaos happens? What is the mechanism behind chaos? So chaos usually happens because of stretching and folding action. Stretching and folding action. So I suggest you can you every day, maybe your mother every day produces chaos in kitchen. but you never notice. Okay, how it is, how it is. So those who make roti, right? So I hope many of you make roti at home. So how you make roti? How you make roti? So you take a bowl, okay, and in that you put wheat flour, right, and you put some warm water, some salt or some oil, and then you start kneading it. You start kneading it, okay. So what happens after that? The wheat flour gets binded with water and makes a consistent dough, right? Consistent dough. And then what happens? If you have used proper amount of water, it will be a good dough. If you have used a large amount of water, it will be like a slurry, like a curry, okay. So therefore, you make a dough, but after making the dough, is that it? Then the roti would be made within 5 minutes. But will roti can be made with 5 minutes? No, it needs time. How it needs time? After you make the dough, again you stretch it. Again you stretch it and fold it back, and again you roll it. Right? You understand? So what you do, this is the dough, and again you put it back inside. Right? And again knead it. Okay, and again take it back and again knead it. Again pull it back, again knead it. Right? So what is happening there? You are stretching it and again you are folding it and again kneading it, right? Why you do that? I mean, your mother always does that, but why? I mean, the moment you make the dough, that's it. Why you again have to knead it, put boxings in it and all? Why you need, isn't it? I mean, why you need to mix it again and again or fold it and knead it? What is the science behind polish? Polish means structure. Why we do that? Hmm. But why? No, the idea is, anyone else want to try? Hmm? But why it increases the taste? If we do that, why it increases the taste? Huh? Batches. Attach. Yes, you mix properly. When you do the kneading again and again, folding, pleating, stretching, folding, you are mixing all the wheat particles with water, and every wheat particle gets required amount of water to be hydrated, and that creates a taste. Right. So you notice that in many food places, so there, like you see, when you make the roti, it is not cooked properly. It is half cooked. So it will be like a rubber, right? So you know it, right? So therefore, that's the idea. Huh? So why you need it? Why you stretch, fold it? So that it mixes properly. So the same idea chaos follows. Same idea is followed by chaos. In chaos, all the face space is again stretched, again folded, again stretched, again folded. Okay, why they do that? So that all the face space in the plane gets mixed properly. This is how chaos is different from randomness. This is how chaos is different from randomness. I mean, in chaos, you can say that this is my 2D plane, and inside this, if you start any point chaotically, then it will totally occupy this whole space. However, this is chaos. However, in randomness, if you they have this whole space and you take points in random, it is not guaranteed that it will fill the whole space. Why? You can start from one point, second point randomly, this third point, fourth point. Then it might be that all points are nearby here, isn't it? Can you see the difference between the two? I mean, it can happen in randomness, right? I mean, no point can fall here. Randomness doesn't guarantee. Does randomness guarantee you that a point should fall here? No, it doesn't guarantee. Randomness can go anywhere. So this is random. So you can see the difference between the randomness and the chaos here. Chaos tries to fill the whole space, but randomness doesn't guarantee you that. Okay. So this is one of the feature. Okay, this is one of the feature or difference between randomness and chaos. Okay, so therefore, when you make the dough randomly, I mean randomly how someone put one thing there, someone put like this, then it is not mixing. You have to properly follow a pattern. So that's how parothas are made, isn't it? That's how parothas are made. So why you think that how parothas are made? Like, yeah. So you can see that the wheat is stretched, right? It is stretched, and then what you do, like it is brought back, and again you make a roll of it, and again you roll it again, bring it back, right? So that's how it becomes more mixing. Okay. So this is referred to as the mixing property. Okay. So this is referred to as the mixing property. Okay. So whenever you have this chaos, you can always see mixing happening. Okay. So all the particles are perfectly mixed. So that's the idea. Hmm? So can we construct? So let us come back to the question. Now that you know what's the difference between chaos and randomness, can you tell me? Can you tell me what is what? How can we construct these 2D maps? I mean, non-linear by adding just simple non-linear term. Any idea? Okay, let us start. Hmm? So you can see I have taken this rectangular sheet. Okay. So not now what I will do is can this what kind of mapping if you apply a non-linear mapping, okay, if you apply non-linear mapping, it transforms to a new coordinate system, say x prime, y prime, and in that you see some different structure. Say this strip has taken this form. What do you think? Is it possible? Is it possible? Now, how can it be possible? So this is possible due to stretching and folding property, isn't it? Stretching and folding property. So what would have happened? Can you imagine what would have happened? I would have stretched this dough on the first step on the x-axis like this, right? So I hope you are visualizing this. So on the first step, you take the green sheet and you stretch it on the x-axis. Okay, then what you do? Then you stretch it on the y-axis, right? I hope you can visualize it, right? Stretch it on the x-axis, then pull it on the y-axis. Then do you get this shape? Yes, you get this shape, right? Now, this stretching and folding, what kind of mapping can cause this? What kind of mapping can cause this stretching and folding? So what we did, we stretched this green part like this, and we pulled it from the middle on the y-axis. So then it became this parabolic kind of shape. Okay, and it is parabolic. I gave you an idea already. So it should have a square term. It should have a square term. So how this stretching and folding? So what mathematical map can show this behavior? That's my question to you. Okay. So you can see that uh, this x-axis, this length of x-axis has been kept same. You can assume that. Okay. So therefore x prime has not changed. That is means x prime is equal to x. However, y prime has changed. Y prime has changed, right? How y prime has changed? You don't need to worry about this. It's just that there will be a square term. Okay. So details you can know later, but it will be something like this. 1 plus y minus ax square, right? Suppose, I mean, you don't need to know why 1 is there, why y is there, why ax square is there. The idea is like this kind of function, if you apply, it can give you this behavior. I mean, nicely. Okay. So you can see there is an x square term. So as you told, as you predicted, we need a x square term as a simple nonlinear term to keep it. So we kept it. Okay. So this is the behavior. Now you do further iterations. You do further iteration. That is, you can make it more skinny. You can make it more skinny. Okay. So what you do, if you take a dough, you make it more skinny, right? You make it more skinny. Why? Because if you want to make puri, what do? You pull it out. You cannot have this big dough for puri, right? What you do, you pull it out so thin so that you will get tiny balls, and those tiny balls will get very, you can roll it and they will get into a disc shape that you can fry, then it will be like a puri. You can put it with your palm. Okay, that's like a puri. So you have to squash it. You have to squash it. Now, how can you squash it? That's my question. So squash it along x-axis. Okay. So that means making this dough skinny, more skinny. So how can you do this? To do this, again you take this xy coordinate system, say x double prime, y double prime. These are the new coordinate system, and you make it more skinny. That means like this. Okay, this is more skinny, right? So how can you get this skinny property? So for that, you are squashing along x-axis, and that you can achieve by making another magnification factor b x prime, right? So, and you can say b is less than 1, mod b is less than 1. So it will be contracting, right? Now, how can we do this? Like another expression you can do further is rotate it, right? I mean, why, I will tell you. Okay, so this is like re-injecting x and y so that we get a boomerang like elongated shape. Okay, so this is like a boomerang, right? So what we do is we do this shape now. Okay, we do this shape now. Okay, how can this be achieved? How can this be achieved? How can this step be achieved? You switch x and y coordinates. You transpose it. You just transpose it. So how? So this will be further will be sorry, y triple prime. This will be x triple prime. So x triple prime is nothing but y double prime. Y triple prime is nothing but x double prime. Right? This is like just like transposing. Hmm? Just like transposing. So my question is, you see how the number of steps we went. Okay, how the number of steps we went from the first step to second step to third step and then to the fourth step, isn't it? How we went. Okay, so you can see first we so visualize. So first we took a sheet, then we elongated it on the x-axis, stretched it on the y-axis, you got the boomerang, right? And you made it more skinny by contracting it on the x-axis, more skinny and more longer. Okay, and then what you did, you rotated it. Okay, so you can easily see how this one shape has been transformed to the fourth shape, right? So this is what Henon has planned. This is what Henon has planned. Suppose this mapping is T1, this mapping is T2, this mapping is T3, then the Henon map T is nothing but the composition of these maps. Okay, that is T1 compose T2 compose T3. Okay, so this is the new map, the Henon map, which can capture all the transformation that leads from step 1 to step 4. Okay, fine. So this is what Henon has done. This is what Henon has done, and it is quite popular also. This has been termed as the Henon map. Okay, this has been termed as the Henon map. So Henon map. Okay, this is known as the Henon map, and I will show you a website which actually shows the animations of this Henon map and how it is happening and why you see this kind of a shape. Okay, fine. So before we go there, just some notations we will follow. Okay, so you can see this is suppose n. Okay, n is your domain. N is your domain, original domain. What you do when you apply the map f? So f is our mapping, right? F is our mapping. Hmm? F is our mapping. So what you do when you apply f, the function to the domain n, so you what will do? What is a function does? Function takes an input, gives an output. So if you give a point to a function, what the function will do? It will return another point, isn't it? This is input, this is output. This is what function does, right? Now instead of a point, if you give an area, instead of a point, if you give an area to a function, what the function will give? Another area, another area. This area is nothing but collection of points. Okay, So those collection of points will be transferred to some collection of points. So that will be another area, right? So how it may be, the area looks like this, right? Area can look like this, right? You can also take a volume. You can also take a volume. That's again a collection of points. You can again pass a function. So volume of points will again be transformed to another set of volume of points, right? So what will happen? You will get another volume. You will get another volume. Maybe something like this. Maybe something like this, right? So this is the role of a function, right? So this is what it does. So when you have a domain n that you can see on this boundary over here, right? This is n, and you apply the function f, right? And you get this area, and you get this green area. So what do you think? It has contracted or expanded? Contracted. It has contracted, right? So therefore this mapping will, so this, in this case, f will be known as a contraction mapping. In this case, f will be known as a contraction map, right? Now check other case that you have started from this n over here, where this is the original part of n. Now you have applied f to that n, and you are getting this area, and you are getting this whole area, right? So what do you think? What has happened? Has it expanded or contracted? It's expanded. So f is referred to as the expanding map. Okay, it's an expanding map. F is an expanding map. So here, what is happening? In this case, something interesting happened, right? If you have this area in green here, right, and you apply the map F, what you see? It has contracted on this direction. It has contracted on the x direction, right? It has contracted on the x direction and has elongated on the y direction. And has elongated on the y direction, isn't it? Do you agree? It has contracted on x direction, then elongated on y direction, right? So here both expansion and contraction are happening. Both expansion and contraction occurs. Okay, fine. I hope that is clear. Okay, fine. Okay. So let us come to this. So the map you just saw, that I told you about Henon map. So this is where Henon has proposed the map. This is where Michael Henon had proposed the map. So a two-dimensional mapping with a strange attractor. So he did an independent study and published this in 1976. Okay, so you can see how he has published this in 1976, and he has written, this is his paper title, a two-dimensional mapping with a strange attractor. So the idea which we discussed now, and you told that it is x square. Okay, before I tell you that it is Henon map. Okay, so this idea he had got in 1976. Okay, got that. So you can see what he has written, that Lawrence 1963 has investigated a system of three first order differential equation whose solution tend towards a strange attractor. Okay, strange attractor are like the chaotic attractors, okay, which has a strange shape. So we show the same properties can be observed in a simple mapping of the plane defined by this mapping, you see. So this mapping you are seeing right now, here is nothing but the Henon map. Okay, so you can see there is a x square term. There is an x square term, right? So there is an x square term, and you can see that due to this, you see something like a parabolic shaped attractor. Okay, so numerical experiments are carried out for this value. Okay, numerical experiments are carried out for this value. Depending on the initial point x0, y0, the sequence of points obtained by iteration of the mapping either diverges to infinity or tends to a strange attractor. Okay, so that's the idea. So I want to, shall we do a coding assignment here right now in the class? I mean, it will be pretty interesting. Before we jump in directly to a website which shows us the animation, only then you can easily understand what is really happening here. Okay, so the idea is, in Python right now in the class, what you do, I suggest, is you create two arrays. Okay, x and y. Fine. You create two arrays x and y. Fine. Okay. What's the size of the array? What's the size of this array? It's up to you. Okay, it is up to you. Maybe you can go up to, the length can be capital N, and capital N can be 10,000 or even 1 lakh or even 1 lakh iterations. So you do what, that many iterations, right? So what you do, what you need to do, select the initial point. The initial point of the array, say 0.1, and initial point of the y variable 0.2, right? And then use a for loop. Then use a for loop, that is for I is equal to 1 to capital N. Okay. What you do, x I plus 1, that is x future variable, right? Because you know the x0 and y0. What you need to know, x1, y1. So xi plus 1 is nothing but the Lorentz system over here, equation 1. That is y of I plus 1 minus a times x of I squared, right? And yi plus 1 is equal to b times x of I. Okay. So this is the idea. Okay. And you end it, right? So by this, by the time it comes to this place, when this routine has passed, check passed, so what will happen? You will see x array and y array already done, right, with number of iteration. I just want you to plot x comma y, both of these arrays with a black dot, okay? And I want you to visualize on this xy plane how the sequence. So what will happen, you will plot those 10,000 points, right? Isn't it? Indirectly you will plot those 10,000 points. Do you understand? You understood. So can you show me the output? So definitely you will ask me, sir, what will be the value of a and b? Okay, we will take the value of a and b as set here, right? So let us take a to be 1.4 and b to be 0.3, and let us see how it looks like. Okay, can we do this coding assignment, right? I mean, you should get a feel of doing this so that you can admire the chaos. So what we saw after you did the simulation is that some, like when you iterated the 2D map, you started with some initial conditions, say x naught is 0.01, y naught is 0.01, right? And then you found that yes, it landed to some Henon attractor. It landed into some Henon attractor, right? Some attractor, right? But in some other initial condition, like someone said 0.1, 0.5, right? It went to infinity. Right? So therefore, you can see that some initial conditions lead to the Henon attractor, okay? Henon attractor, whereas other initial conditions make it diverging, okay? Make it diverging, fine? Make the attractor look diverging, right? So this motivates us to ask the question, which initial conditions lead us to the attractor and which initial condition makes it divergent, right? You understood? So as you saw, some initial condition leads to that attractor, some other initial condition goes to infinity. When you are not getting a plot, the values are going to infinity. What you can do to know whether they are infinity or not, you can try to write if it is infinity, if it returns true, or you can plot the numbers and check. Okay, so therefore the question is, which initial condition leads to the attractor? We want to know which initial condition leads to the attractor. To do that, what you will do, can you computationally think of an idea, how can we find which set of initial condition can lead us to the chaotic attractor and which of the initial condition doesn't lead to the chaotic attractor? Can you computationally do that? To do that, what can we do? we can adopt an idea, and this is that idea, that suppose we have x naught and y naught. Suppose we have x naught and y naught. Think that this is a grid. Okay, think that this is a grid. Okay, what I do, I make a very fine grid. I make a very fine grid. Okay, I make a very fine grid, and such fine grids, like you can see, these are the fine grids, right? This is the fine grid, and with this fine grid, what I do, if I take this initial condition over here, and this leads to an attractor, I can mark it blue. If this initial condition leads to an attractor, I mark it blue. Suppose this initial condition doesn't lead to the chaotic attractor, rather diverged, then can make it red, right? So what you will get? You will get a collection of blue and red pixels throughout. So usually such structures will lead to a fractal. Okay, will lead to a fractal. Okay, and such an idea of making this heat map is known as basin of attraction. Is known as basin of attraction. Okay, is known as basin of attraction. Fine, that's the idea. Okay, we'll see that. We'll see that. So how the Henon attractor looks like? You can see the Henon attractor looks like this. Okay, the Henon attractor looks like this. Fine. So you can see this is the x coordinate, this is the y coordinate. Okay, and you can clarify that yes, you are getting some attractor like this. Okay, how this attractor is being constructed? One point will be here, the next point can be here, next point can be here, here, and so on. Then as iterate progresses, you get this 2D Henon chaotic attractor, right? Now what to do after having this chaotic attractor? So what you do is just try to zoom into this small portion. If you try to zoom into this small portion, you got this bigger version picture here. So you can see this picture here is looking like this. Now what you do, take this small portion here and zoom it and make a zoom. So what you get some structure like this. You get some structure like this in the C figure. What you do again, you take a zoom of this figure, okay, and how it looks like this, okay. It looks like this, okay. This is the D figure. So you can see how much you zoom, you get similar kind of structure again and again, right? So what does that remind you? If you zoom in more and more and you see similar kind of structures. Yes. So this Henon attractor is a fractal. This Henon attractor is a fractal. Of course, when you zoom this, there might be small points, but if you have taken larger set of points, it will always be the same pattern. Okay. So you can see the same behavior is seen here and here as well. Okay. So therefore, Henon attractor is a fractal. Okay. Henon attractor is a fractal. So we'll see this. We'll see this. Now I asked you a question. That which initial condition lead to chaotic attractor, which initial condition goes to divergence. Okay. So you can clearly see what this plot. This is done in computational way. This is a heat map. Okay, it's a heat map. What does this heat map give us? You know, in Henon map, you have two parameters, A and B, parameter A and parameter B, right? So as you vary parameter A and B, you get periodic solution, fixed point, chaotic attractor, it might diverge, right? Now you want to know which parameter gives me fixed point, which parameter gives me periodic point, which parameter gives me chaotic orbit or chaotic attractor, which parameter gives me unboundedness, that means diverging trajectories, right? So in order to do that, you, as I suggested, you make a fine grid. You make a fine grid, right? You make a fine grid like this, right? You make a very fine grid. Then what you do, if you get, suppose you took this parameter point, then it gives you this fixed point, then mark it blue. If this iterate gives you, periodic point, mark it red. If this point, parameter point gives you chaotic attractor, mark it black. Again, if this gives you a unbounded solution, mark it white, isn't it? So yeah, but don't connect the lines. I mean, the points you're connected by a line, don't connect by line. Just make it discrete point. Point to point. No line should be connected between. So then you will get the structure. Okay. Why we don't connect the points? We don't connect the points because it is not a flow. It is not continuous. Okay, it is not continuous. It's a discrete map. So it jumps from one point x naught, you apply f, it jumps to x1, that is f of x naught. X1, you apply f, it goes to x2, right? X2, you apply f, it goes to x3, right? So, got the idea. So, therefore, we never connect these dots. We never connect these dots. Connecting dots we can do in ODE, differential equation, 1D flow, because the solution is like this, we feel, right? Oscillations. So, here you see discrete points, here you see discrete points, and hence the mapping is known as a discrete map, right? Whereas this is continuous, hence you know call it as a flow. Okay, here you call it as a flow, like 1D or 2D flow. Okay, that's the idea. So this is how computationally you can get a graph. Which parameter combination can give me fixed point? Which parameter combination can give me periodic point? Which parameter combination can give me chaotic point, right? Now, see very carefully that in this region there is a periodic fixed point, right? Then if you increase the parameter, you see a boundary here, right? You see a boundary here, which you can see easily. This is a boundary, right? In this boundary, when you cross this boundary, you enter periodic point, right? So this represents a change in the dynamics of the map. So what does it should correspond to? A bifurcation. When there is a qualitative change in the behavior of your system, it is referred to as a bifurcation. So therefore, when you vary parameter along this direction, from fixed point, you increase the parameter and then suddenly you go to periodic point. So there is a change in the behavior of the system. So therefore, this is referred to as a bifurcation. This is referred to as a bifurcation, right? Got that? Fine. So this is a Henon map, right? So similarly, you saw how Henon map looks like. This is the Henon attractor. So this is the Henon attractor, right? This is the Henon attractor, how it looks. So now you see how a 2D mapping can give you a very nice structure like this. So after Henon, people thought that why we have to use a cubic term. We can use why we have to use a square term. We can use a cubic term. We can use a fourth order term. We can use sinusoidal terms. We can use fractional terms, right? Many things scientists have suggested. Due to that, they started to see many different and new figures. Okay, so therefore this is what I wanted to show you the previous class. Okay, so when scientists and researchers tried different maps, what they do as a mathematician's mindset or researcher's mindset, what they did is they wrote a general equation, that is xi plus 1 yi plus 1 is equal to some a naught plus a1x plus a2x square, right, plus a3x cube, so on, a4 x to the power 5 4, so on till say a100 x to the power 100, right? Similarly, you do the same thing for b, right? And what you do, you vary computationally. You have a lot of variables, right? You vary a0, a1, so on, a100 vary. So you can see each can have say 100 combinations. So you can see how many number of combination it can be. Each has 100 combinations. So 100, 10 to the power 2, 10 to the power 2, like that 100 times. Like that 100 times. So many combinations. So when they swapped into lot of combinations, because you don't know which parameter value and which power of the map can show which kind of a different figure. So they surveyed a lot. And you can see below they came up with these unique structures. Okay. And you can see it is very difficult to see here. But you can easily see that here, like here on the top, say here, right? You can easily see the parameters mentioned, but it is very tiny and you cannot see it. But if you can get this book, you can easily see this. Okay, you can easily see this. Okay, so there they have considered 2D quadratic maps and 3D ODE system. So written by Sprott and Eldhaj. So it's a book, right? In that book, you can see all these nice chaotic attractors. Okay, and you can clearly see that it is not random at all. I mean, even though they behave like in a very chaotic order, still they have a structure to it. Still they have a structure to it. So this is what people started calling it order from chaos. Order from chaos. Okay, or order in chaos. I mean, in chaos also there is an order. In chaos also there is an order. So you can easily see that the structures are very good. Anyway, so let us be back. Hmm? So what we can do is right now is I can show you the Henon map here. Okay. So this is a very nice website. This is a very nice website. Hmm? There is a yeah. Okay, so this is a nice website. Okay, this is a nice website where which I found and where very nicely the animations for Henon map and everything is presented. Okay, so you can see this Michael Henon sought to recapitulate the geometry of the Lorentz attractor in 2 dimensions. Okay, and this requires stretching and folding of space achieved by this 2D system. I already showed you this, and we took this parameters also, right? So they are plotting using Python, like you can see matplotlib and PLT in a dark background, and you can look into this code. Okay, you can see they are iterating that same thing, return, and they are returning the next point. Okay, or every time they iterate, and they are using how many iterations? Once, 100,000, 1 lakh, 1 lakh iterations, and they are starting from the initial condition 0, 0, and you can see this is how they are iterating that Henon attractor map. Okay, so and they are plotting it, okay, with white dots. So in the black background you will see white dots. Okay, and that's it. So you can see this is how the Henon attractor looks like. Okay, so you plotted black points in the white background. He has plotted white points in black background, so it looks better. Okay, so you can see it looks even nicer, right? So let us see how does the equation produce this map. So you can pause it. What you can do at every iteration when it plots, you can hold it for 1 second or 2 seconds before plotting the next point, so that you can visualize how the points move in the space. Right. So now what you see just the attractor, because the points are getting plotted very fastly. So if you pause it, okay, if you pause it, you can see how these points are getting plotted here. You can see. Okay. I hope that is visible there, right? You can see how this plot, even now it is very fast. Even now it is very fast. So what I suggest is, if you try to do, then what I suggest is you try to pause it for more time, maybe 2 seconds, 3 seconds more, so that before plotting it will be very slow and you can see how that attractor is being plotted, how the attractor comes to life. Okay, so you can see how the attractor comes to life, right? So this is the Henon attractor, right? So fine. Now, I also told you that Henon attractor is a strange or a fractal attractor. Why? Because you can see that even you zoom more and more parts, okay, more and more parts of it, it will behave the similar way. See the zoomed part, right? Again, you take the zoomed part, it will be the same behavior, right? Again, you zoom part, same behavior, right? So that's the Henon attractor. So let us see this video actually, where you can easily see how the Henon attractor zoomed case looks like. Okay, when you keep on zooming this Henon attractor, so you can easily see that we are entering into the zone. Yeah, you can see now the fractal property has started to appear, like you will see the similar behavior, similar set of lines and curves like dots, again repeating. Okay, so you can see. So these are finely stretched out. These are finely stretched. Okay, so you can see it is still zooming, and you are seeing the similar kind of things, right? So this is therefore this is a fractal. Okay, fine. So you can see. I told you that some of you tried that some initial condition gave you a chaotic Henon attractor, and some initial condition gave you a diverge to infinity, right? So we wanted to know which initial condition gave strange attractor and which initial condition gave chaotic attractor, right? Or which initial condition diverged, right? In order to do that, we have to see something known as the basin of attraction. That's like a heat map plot on the set of initial conditions, right? So you can see that some experimentation can convince us that not all starting points head towards the attractor upon successive iterations, right? This you can agree. Hmm? So instead, some head towards positive or negative infinity as well, right? So the collection of points that do not diverge or head towards infinity for a given Henon map is referred to as the basin of attraction. Okay, is referred to as the basin of attraction, right? So basin of attraction may be a fractal or else smooth, as shown by York. Okay, so the York is a scientist who has studied more on fractals. So the idea is, does the Henon map with this chaotic attractor, that is A is 1.4 and B is 0.3, have a smooth or fractal basin? That's the question. Whether they have a smooth or a fractal basin. To find out, they have studied, they have coded it up. They are doing a heat map. You can see from -5 to 5, they are doing around, you can see 2000 points. Okay, in between that lens space. Okay, they take in between two, sorry, they take 2000 points in between -5 and 5. So that's how they are making a fine grid. On X, they are making that grid. On Y also, they are making that grid. So you get a 2000 cross 2000 set of points, right? So you can see when you do that, when you run with the code, you come up with this. You come up with this diagram when you make a heat map plot. Okay. So you can clearly see that this is the chaotic Henon attractor here, and all these points in the dark background here, okay, can lead to the chaotic attractor. Whereas other points, if you take and iterate, they might not converge to the chaotic attractor and will diverge. And you see how complicated the basin looks for a larger number of iterations. You can see this looks like our solar system or galaxies, and you can see how they have a correspondence. I mean, if you see a galaxy, they seem like they are mixing. Okay, and this mixing property, you can see, yeah, now, right now, yes, you can see these are the mixing properties there, right? How it is getting mixed. Okay, so you can see this. Okay, so this is a short view of that. Okay, if you iterate it more and more, so this is not possible if by without using a computer. So this you have to do computational experiments to achieve this, and this takes a very nice amount of time to achieve. Okay, very nice amount of time to achieve, because a lot of graphic ideas and systems you have to follow. Okay, but I suggest you should read this website to know more how they are plotting such beautiful diagrams. Okay, and what kind of plotting tools they are using. So it will be really interesting to understand. Okay, so that's it about this Henon. And in Henon map also, you see this period doubling bifurcations also. Okay, so you can see how this diagram looks like, very nice, because they have plotted in the black background, and you can see this is a period doubling point. Again, you see some period doublings again and again, right? See, here it is a period doubling, here it's a period doubling, and it is going on forever. It is going on forever, right? So that's the idea. That's the idea. Okay, I suggest you read this website. Okay, I will I will put this, and he has suggested, he has drawn a lot of things about this Henon attractor. Okay, which is quite interesting. And I suggest that you should know how the plotting tools work in Python to achieve these beautiful set of animations and diagrams. Okay, so fine. So you can see the fixed points, There are a lot of attractors. Okay, so yeah, what these figures mean, right? So I have not checked, but it is something like uh, they have mentioned. I don't know, Draga or something. Mm, let us go. Let us see. I saw this morning. Mm. Yeah, but uh, they are using some other library also. Hmm? I think it is same matplotlib only. So you can see using matplotlib how they have achieved this. I mean, pretty interesting. Okay. So you can see just we started with a tiny looking equation. Okay, we just started with a 2D map and it is non-linear, just a square term. And this nonlinear map is showcasing you such fractal diagrams and such beautiful diagrams. So this gives us an idea that a simple nonlinearity can showcase a lot of chaotic attractors and diagrams to you. So this is one of the ideas. And same, you can have different attractors also. This is Henon is not one of the attractors. Okay, Henon is not one of the attractor. There is something known as Clifford attractor also, devised by Clifford. Here, people thought that why we will use x square term. What happens if we use trigonometric term also? I mean transcendental terms. So when they use transcendental terms instead of squares and cubes, they found that you see some attractor like this. You see attractor like this, which is very interesting. Which is very interesting. I mean, how these you see here the denseness of the points is high in here in this space, in the 2D space. Mind you, this is not a 3D diagram. Mind you, this is a 2D system. Why it's a 2D system? You can see this is a 2D system, x and y, x and y. So here you can see a 2D system, but you can see here very less set of points are there, whereas here there is a high density of points. Here there are high density of points, right? You got the idea. Hmm? So how the attractor looks like? So this is the Clifford attractor, which is very different from Henon, right? Don't think that these are curves. These are a huge collection of points, points lying close to each other, which makes an appearance that they are joined by a line. But actually, when you zoom in, these are just points very close to each other, making a perception that it's a curve. Okay. So you can see Clifford attractor are also fractals. Okay. So you can see the zoom in. When you zoom and zoom, you can see this part is nothing but a part of a Henon attractor. Does this remind you a part of is a Henon attractor, right? So you can see more and more you zoom, it's like a Henon attractor. And do you know that Henon attractor is a fractal? Yes, you know Henon attractor is a fractal. So when you zoom and zoom into Clifford attractor, which takes the shape of a Henon attractor, and you know Henon attractor is a fractal, so therefore Clifford attractor is also a fractal. Okay. So therefore, Clifford attractor is nothing but whenever you zoom in the Clifford attractor, anything like that, you will always come to the basic part, that is the Henon map. So Henon map is like the simplest 2D map which can show you chaos and fractal behavior. So therefore, however sign terms you use, you will always find yourself in using the Henon map. Why Henon map could have come? Because these are having sine and cosine terms. You know, sine and cosine terms, when you expand as a Taylor series, they have all functions, x square, x cube, x fifth, and all. So therefore, indirectly, x square terms are hidden inside. So therefore, indirectly, you are bound to see some Henon chaotic attractor, right? So you see, even on the smaller scale, zoom and zoom, you are still seeing these kind of plots. Okay. So that's the idea. So you see periodic points here, right? These are periodic points. These are periodic dots. Okay, these are periodic points, finite set of points. The more and more you zoom in, you can still see different attractors here. And yeah, this I think as parameter vary, you can see how they combined with each other. How they combined with each other, isn't it? So how they combined with each other and made this diagram possible. Do you agree? Right? So this is about all about the Clifford attractor, and you can see this is another beautiful plot. Another beautiful plot where we see these kind of diagrams. Okay, and yeah, that's all about this. So fine. Hmm? Okay, so you can carry on with this, and yeah, maybe next class we can do something. Okay, fine. Okay. So next class maybe we can carry forward with this some properties of Henon map. Like uh, for now we have just seen how a Henon map looks like, how the chaotic attractor looks like. There in the next class we will derive some property. I mean, is the Henon map invertible? When can Henon map expand? Is the Henon, how can you compute fixed points of Henon map? Right? So yeah, that's that.